an input lens were pillboxes waiting for an unsuspecting advancing infantry. The result could be devastating. But to make it all work,
100 years ago, a deceptively simple formula revealed a hidden unity buried deep in the fabric of the universe. It tells of a fantastic connection between energy, matter, and light. Its author was a youthful Albert Einstein. It's the most famous equation in the world. E equals mc squared. But while we've all heard of Einstein's big idea, very few of us know what it means. In fact, E equals mc squared is so remarkable that even Einstein wasn't sure if it was really true.
Albert, darling, you're later than I expected. We've only got sausage and cheese tonight. What is it?
We need to talk.
Has something happened?
Oh, no, nothing. Sorry, no. I spent most of the day staring out the window at work, looking at trains. And I started to think about an object and how much energy it had. Can I explain it to you?
Of course you can. But first, dinner, food and talk.
I think the gods are laughing at me.
The gods were not laughing at Einstein. He united in one stunning insight the work of many who had come before him, scientists who'd fought and even died to create each part of the equation. The story of E equals mc squared starts long before Einstein with the discovery of E for energy.
All right, so let's get back to this special relativity. So it's a special case of motion near the light speed at constant velocity. So you don't get to speed up, slow down, or change direction. So everything that we were discussing is true near the light speed. So special relativity. This is. All right, so the theory was published in 1905. It's a specialized case of motion near the light speed. So you're moving approximately near the light speed. So moving in a straight line at a constant speed. So the motion by definition is a space around mass in space and in time. So something is going to happen to time, something is going to happen to space, and something is going to happen to mass. That's what it means when you start to move near the light speed. All right, so if something is nuts.
Headaches and migraines that will start for 10 years. So ask your doctor about those drugs today. I've never seen anything like this.
Okay, so according to the first postulate, motion is going to be near the light speed in a straight line at a constant speed. So the motion is going to happen at a constant velocity. So D is the best answer.
Imagine if I was sitting still and holding a mirror to my face.
All right, so everything goes back to this question again. He says, what if I'm traveling at the light speed with a mirror in my hand? Would I be able to see my reflection in the mirror? All right, so this time we will do the same thing, a little bit more mathematically. So classical relativity is the way we will look at things. All right, so this reference frame is moving at 50 miles per hour, and the ball is also moving at 50 miles per hour. Okay, so will this ball ever reach this reference frame, moving away at 50 miles per hour? The answer to that question is no, right? It's not going to be able to reach this reference frame. All right, so this thing is moving away at 50 miles per hour. The ball is also moving at 50 miles per hour. So this ball will never reach that reference frame. Okay, so now this ball is within this reference frame. And this reference frame is also still moving at 50 miles per hour. And the ball is still moving at 50 miles per hour. All right. All right, so postulate number one is going to say the laws of physics are the same in every single reference frame. Inertial reference frame. Inertial reference frame is a reference frame either at rest or moving at straight line at a constant speed. And then we got the stationary observer outside. And the stationary observer is going to be looking at this ball. And this is, all right. So what is the speed of this ball with respect to the stationary observer? Okay, so what you need to do is you need to take the speed of an object, and then you need to add the speed of the reference frame and add up these two speeds. And that's all you have to do, just add up these speeds. All right, so now you have to kind of focus on, okay guys, just wait for a second. I gotta change the battery.
Stranded on an old set of overgrown tracks are rail carriages that tell of a troubled period in Hungary's history. The later stages of World War II.
All right, so at this point, the symbols are going to matter. So I just want to be in control of the lecture. This is not an art school physics lecture at this point. Okay, good. Because we need to start focusing on the symbols. Okay, that's interesting. All right. Okay, so u sub x prime. All right, so let's go forward. Okay, so we got the postulate number one. Okay, so u sub x prime is going to represent the speed of this object relative to a reference frame moving at the speed. So v is going to represent the speed of the reference frame relative to an Earth reference frame that we're looking at. This is the speed relative to the stationary reference frame. All right, so this person is on a stationary reference frame. When we say a stationary reference frame, it's like your reference frame, my reference frame. We're not stationary, but we feel stationary. You're looking out, you see this spacecraft moving at 50 miles per hour, or a car moving at 50 miles per hour. Inside the car, you see a ball moving 50 miles per hour relative to the car, all right? So what is the speed of this ball relative to you if that's the case? So you add this speed to that speed. So just remember this u prime of x that you're looking at, u prime of x is going to be the speed of the moving object in a moving reference frame, in essence. So now we're going to be interested in the speed of this object relative to us. So this u of x is going to give us the speed of this object relative to our reference frame. So which means that you take its speed in a moving reference frame and then add the speed of the moving reference frame to it. So that's the way we would do it. So it's going to be 50 plus 50. So it's going to be 100 miles per hour. All right, so this is known as a Galilean transformation. So we're just adding up the speeds. So it's speed of the object moving inside relative to your moving reference frame. And then we're interested in the speed of the moving reference frame relative to us. So this speed plus that speed is going to be the speed of this object in our reference frame. All right, so moving forward. So according to the second postulate, the light is going to move at the light speed relative to every single observer. All right, so relative to you, regardless of your motion, light is always going to move at the light speed. So Einstein's nose, mustache, the light is a particle moving at the light speed towards the mirror, which is also moving at the light speed. Once again, I got my stationary observer here. All right, so here's the speed of light relative to this reference frame. U of x prime is going to give you the speed of light in this reference frame. And this reference frame is moving at the light speed relative to this observer, the stationary observer. So the question becomes, what is the speed of light relative to the stationary observer, this particular light? So once we will once again do the Galilean transformation. That's the commonsensical way of transforming stuff. All right, so we got the light speed relative to this reference frame. So the light is moving at the light speed relative to that reference frame. And that reference frame is moving at the light speed relative to us. So what we end up getting is c plus c, so it's going to be twice the light speed. But the problem with that is light should move at the light speed relative to this guy, Einstein, as well as this guy, the stationary observer. All right, so which means that light cannot be moving at twice the light speed. So which means that the Galilean transformation does not work, which means that the normal standard map that we've been using, the commonsensical map is not using, is not going to work for this sort of stuff. Now, according to postulate number 2, the light moving at the light speed relative to Einstein while he's moving at the light speed relative to us should still move at the light speed. All right, so this is the postulate number 2. And then we should come up with the map that's going to agree with that. All right, so the commonsensical method we've been using, the Galilean transformation, is not the way to do this. So the question is, what kind of method are we going to use? All right, so
Your audio is distorted.
so let's fix that.
The Hungarian locomotives and rollings
Is it better?
are stripped out and shipped.
Yes.
All right, give yourself 5 points. All right, so this guy to the rescue under the circumstances. Lawrence. All right, so Lawrence is one of those guys who believed in the existence of ether. Remember the Michelson-Morley experiment proved that there was no ether? Now, all of a sudden, he's thinking, wait a minute, the ether is there, and there's a reason why we're not able to detect the ether. Because more than likely, in the direction of motion, the instruments are contracted. So it comes up with these transformations, which are known as the Lorentz transformations. All right, so this guy is in 1902 Nobel Prize winner. He comes up with the mathematics in order to rescue the theory, the concept of ether. Except Einstein looks at Lorenz's work and he goes, oh, this is the sort of mathematics I need to rescue my own theory of special relativity. All right, so here's what Einstein does. Einstein knows intuitively that there's no ether, but all of a sudden he sees the value in the sort of mathematics that Lorentz came up with. All right, so these are known as the Lorentz transformations or Lorentz transformations. Okay. All right, so u of x prime is going to represent the speed of an object in a moving reference frame. This represents the speed of the moving reference frame. And this is the speed that we will measure for this object in this reference frame. All right, so all of a sudden we end up getting a more involved transformation than the Galilean transformation. All right, so we're looking at the speed of an object inside a moving reference frame. And this moving reference frame, V, is moving near the light speed relative to us. All right, so here's the light moving at the light speed in this reference frame. And this reference frame is moving at the light speed relative to us. All right, so u of x prime is the speed of light in a moving reference frame. All right, and this is the speed of the moving reference frame. Speed of the reference frame moving relative to us. All right, so we'll go back to this equation and then just insert these values. So u of x prime is going to be c, plus this reference frame is also moving at the speed of light, so this is going to be c. So this is c, so is this one. So we end up getting c squared divided by c squared, and then you have two c's in the numerator. So c plus c in the numerator plus 1. You have c times c, so it's going to be c squared here divided by c squared. So 2c plus divided by 1 plus c squared divided by c squared. So this is going to be 1. 1 plus 1 is going to be 2. 2 divided by 2 is going to be 1. And then boom, Galilean transformation worked out. So this light moving at the light speed relative to this reference frame, while this reference frame is moving at the light speed relative to us, this light is still going to move at the light speed relative to us. As it so happens, Einstein discovered that this Lorentzian transformations is exactly the sort of mathematics that he's looking for. And all of a sudden, this is the sort of mathematics that agrees with him. He just grabs it and starts using it. He uses it, he abuses it, he just grabs the math right under Lorenz's nose. Because Lorentz tries to rescue the theory of ether, and Einstein goes, nope, nope, there's no ether. But this is useful. Because Einstein wants to make sure that every single person experiences the same light speed. Same light speed. Relative to each and every single person, the light is always going to move at the light speed. And he was looking for the math, and then he discovers this in Lorenz's mathematics. It's amazing. All right, so that's the Lorentz transformations. All right, so that's it. Okay, let's take a look at an example of this. This is going to be fun. All right, so let's assume that we have an object moving at 88% of the light speed. All right, relative to spacecraft. All right, so the object is moving at 88% of the light speed. Relative to spacecraft, we're moving at 60% of the light speed to the Earth reference frame with respect to the Earth reference frame. All right, so object is moving at 88% of the light speed relative to the spacecraft, and this spacecraft is moving at 60% of the light speed relative to Earth. So the question is, how fast is this object moving relative to Earth? All right, this is the sort of stuff. All right, so V represents the speed of the spacecraft. It's moving at 60% of the light speed relative to Earth. And relative to that spacecraft, that object is moving at 88% of the light speed. So relative to us, the Earth-mount observers, how fast is this object moving? All right, so what we do is we use the Lorentz transformation formula. So speed of the object relative to the moving reference frame, which is this. Speed of the moving reference frame relative to us. And this is the speed of the object relative to us. All right, so it's going to be, you plug the numbers in, all of a sudden you discover that this object is moving near the light speed, but not above the light speed. It's 96.8% of the light speed relative to us. All right, so that's how example that I came up with
So, while Albert will surely agree
is this example.
that Henry
So Einstein,
throws
Lorentz.
one heck of a fastball, he can always throw a little light on the matter. And be sure it'll get there first.
Even along the direction of relative motion, components of velocity never add to a speed greater than the speed of light.
All right, so nothing's going to travel faster than light. That's what it means. All right, problem number 1 from the handout. All right, so this one is a Star Trek problem. You got the Enterprise traveling at 90% of the light speed. And Enterprise is traveling 90% of the light speed relative to Earth, based on what I'm looking at. And then we have a Klingon spaceship moving at 80% of the light speed relative to Earth. So this one is moving at 90% of the light speed relative to Earth. This one is moving at 80% of the light speed relative to Earth. So the question is, how fast is... All right, so the Klingon from the Earth, 80% of this station relative to Earth. All right, so how fast the Enterprise overtaking the Klingon ship at relative speed? Okay, what is the question? All right. Oh, okay, so this is will be all right. So based on the Earth reference frame, this one is overtaking this one at 10% of the light speed. Okay, that's fine. I thought there was something more, but that's it. All right. So with what speed is the Enterprise overtaking the Klingon ship is seen by the crew of the Enterprise? All right, so we're interested in the speed with which the Enterprise is overtaking the Klingon ship. All right, so which means that we're interested in, all right, we gotta figure this out. I'm trying to figure out what it is. All right, so this is the speed of the Klingon ship relative to Earth. All right, so it's going to be 8% of the light speed. U of x is the speed of an object as measured by the Earth reference frame. And then we're going to be interested in a second reference frame. So we're interested in the speed of this reference frame. So the speed of this reference frame is going to be 90% of the light speed. Okay, guys, so ignore the notations, the symbols here. I'm reversing the symbols because V is going to represent the speed of the reference frame of interest. So this is the speed of the reference frame of interest, which is this. Instead of U, it's going to be V. So this reference frame is moving at 90% of the light speed. And then this object, the Klingon ship, is moving at 80% of the light speed relative to us. So the question is, how fast is this moving relative to that reference frame? So we are interested in U of x prime. So which means that we're interested in the speed of this object relative to the Enterprise. And that's a long explanation. Okay, so which means that there's a second formula that we have to use. Second formula is going to look like this. All right, it's the same as the first formula, except U of x prime becomes U of x plus becomes minus. All right, so this is the formula that we will get to use. Now we're interested in the speed of the Klingon ship relative to Enterprise. All right, so you did the computations, and all of a sudden, relative to Enterprise, we're going to end up getting a number which is going to be negative. So it's going to be about 35.7% of the light speed. It's going to look like the Klingon ship is actually moving towards the Enterprise at that speed. All right, so that's the meaning of it. All right, so this is one of the problems that you kind of have to get a better understanding. All right, so let's take a look at this problem. All right, so we got two rockets, A and B. And so A and B each moving at 90% of the speed of light relative to Earth, and they're moving towards each other. So calculate the relative velocity of B with respect to A. So this is more or less the same sort of problem that we did before. All right, so we got two reference frames. Here's the Earth reference frame. A and B are moving towards each other. All right, so A is going to be our moving reference frame, and B is the speed of the object that we're going to be interested in. All right, so this reference frame is moving at 90% of the light speed relative to our reference frame. Our reference frame, the Earth reference frame, is going to be S. This second reference frame, this is the object whose speed we're interested in. So it's moving towards the Earth, or towards this one, at 90% of the light speed. So how fast is this moving relative to this one? So we're going to be interested in U of x prime. Once again, we will get to use the same formula that we used before for the Enterprise Star Trek example. right, so plug the numbers. So it's going to give us 99.45% of the light speed. It's negative, which means that the other object approaching the first one. So you will have to take a look at those problems.
In order to simplify the problem he sees with light, Einstein uses a series of thought experiments that take place only in his imagination, like a journey on a train.
All right, relativity. Motion near the light speed at a constant velocity. So it's a special case of motion, or a specialized case of motion. Special is used in the politically correct sense. When somebody says special, which means limited. So it's only limited to motions near the light speed in a straight line, and you don't get to change direction. So you don't get to speed up, you don't get to slow down, you don't get to change direction. So it's a special case of motion. Published in 1905. All right, and if you are moving near the light speed, something is going to happen to your mass, something is going to happen to time, and something is going to happen to space. All right, so the theory is about what happens to mass, what happens to time, and what happens to space. This is known as the special theory of relativity. Everything started in Einstein's mind when he was 16 years old. I had a simple question. He was studying the Maxwell's equations, and according to the Maxwell's equations, the light travels at the light speed, right? But on paper, light travels at the light speed relative to some reference point. All right, so relative to our reference point, light is going to travel at the light speed. So what is that reference point? What is the point of reference relative to which the light is traveling at the light speed? So that becomes the question. And so Einstein goes, as far as Maxwell was concerned, there was a substance called ether, and relative to ether, the light was supposed to be traveling at the light speed, but the concept of ether was nonsensical. I mean, Einstein could see it even when he was 16 years old. He's thinking about, what if the ether doesn't exist? What if there's no stationary reference frame relative to which the light can travel at the light speed? So obviously the question becomes, what if that reference point also traveling at the light speed? If that reference point is traveling at the light speed, does this mean that the light still travels at the light speed relative to that reference point? Okay, so when somebody is describing a really abstract concept to you in the fashion that I'm describing it to you right now, you don't really get much of it. All right, so simply put, all right, what if you have a mirror in your hand while traveling at the light speed? Would you be able to see your reflection in the mirror? All of a sudden, that question that Einstein had turns into this question for communication purposes. You're traveling at the light speed, you got a mirror in your hand, you look into the mirror, would you be able to see your reflection? Now, for you to be able to see your reflection, the light from your face has to reach the mirror first. The problem is the mirror is moving at the light speed, light from your face is traveling at the light speed in the direction that the mirror is moving, and your face is also traveling at the light speed. So will the light ever reach the mirror? Common sense is straightforward. The answer is no. Well, nothing about Einstein's thinking is commonsensical. Einstein is thinking, wait a minute, he understands the Maxwell's theory well enough to know that if that point P, a reference point, if that point is traveling at the light speed, the equations still should hold true, which means that light still should travel at the light speed relative to that point. All of a sudden, the question becomes, well, if that light is traveling at the light speed relative to Einstein, while Einstein is traveling at the light speed relative to us, then what happens to that light? Shouldn't that light travel at the light speed? Shouldn't that light travel at double the light speed relative to us? And Einstein is thinking, no. Einstein is thinking light should travel at the light speed relative to everyone, regardless of their emotions. At that point, it's completely counterintuitive. All right, so all of a sudden that becomes this postulate number one. Postulate number two. All right, so classical relativity is the one that we're focusing on. All right, so I'm just going to take you through the logic one more time. All right, so here's an object, a car moving away from you at 50 miles per hour. And then imagine that you're trying to smash the back window because the guy tried to run you over. All right, so you throw a rock in the direction of the car at 50 miles per hour. So this is moving at 50, the car is moving at 50. Obviously, this rock is not going to be able to reach the car. All right, so nothing is going to happen here. So this rock is not going to reach this car. Now imagine that you're on a bus. Bus is moving at 50 miles per hour, and that this rock becomes a baseball in this case. You throw the baseball in the forward direction at 50 miles per hour. Evidently, you're capable of throwing things at 50 miles per hour, right? This is the fastest you can throw something. All right, so it doesn't, this is the speed with which you're going to be able to throw things. Regardless of, this is the maximum speed with which you can throw things. So the speed of the ball is going to be independent of the motion of the vehicle that you're in. All right, if it's a bus, it's moving at 50 miles per hour. If it's an airplane, it's moving at 550 miles per hour. So it doesn't matter. It doesn't matter how fast this vehicle is moving. The fastest that you can throw this ball is still going to be 50 miles per hour. Right? That's what it means. So this motion of this ball is going to be independent of the motion of the reference frame that you're in. All right. So now the postulate number one, the assumption number one says the laws of physics are the same in every single inertial reference frame. All right, so which means that the laws of physics will be the same, which means that if you're outside, this is the fastest that you can throw this ball at 50 miles per hour. Inside a moving reference frame, as long as it's moving in a straight line at a constant speed, the fastest this is going to move is still going to be 50 miles per hour relative to you. So that's the meaning of it. All right, so these are known as inertial reference frames. Inertial reference frame is either a reference frame which is at rest, or if it's moving, it's going to keep on moving in a straight line at a constant speed. So which means that whatever happens here is going to be identical to whatever happens here. That's the meaning of it. So that becomes the postulate number one. Once again, the postulate means assumption. This becomes the first assumption. All right, so Einstein is setting up his own assumptions under the circumstances, and then he's going to build a theory based on these assumptions. All right, instead of saying assumption, he's saying postulate, because the postulate has gravitas. It sounds a lot more important. All right, so imagine that we have a stationary observer outside who's capable of seeing this ball. It's also capable of seeing that ball at the same time. All right, if he's looking at this ball, this guy is stationary. This ball is going to move at 50 miles per hour relative to this guy. And then now he's looking at this ball. This ball is going to move at 50 miles per hour relative to the bus. And the bus is moving at 50 miles per hour relative to him. So this ball is going to be moving 100 miles per hour relative to the stationary observer. All right, so the laws of physics are still valid under the circumstances. So u of x prime represents the speed of an object relative to a moving reference frame, which is this. And v is going to represent the speed of that moving reference frame relative to the stationary observer, which is this. And u of x is the speed that this guy is going to measure for this ball. All right, this is known as the Galilean transformation. All right, or instead of complicating it, I mean, commonsensically, the ball is moving at 50 relative to the bus is moving at 50 relative to each other. You're adding up the speeds. I'm using this so that you have an understanding of the symbols. So u of x prime is going to represent the speed of an object that you're interested in relative to your moving reference frame. V is going to represent the speed of the moving reference frame relative to you, and u of x is going to represent the speed of the object of interest relative to you, in essence. All right, so that's what it means. All right, so this is known as the classical relativity or Galilean transformations. All right, so the second one is a relativity postulate. It goes like this. All right, so here's light moving at the light speed relative to Einstein. Light is moving at the light speed, the mirror is moving at the light speed. Einstein is also moving at the light speed. So one thought is, oh, it's not going to be able to reach the mirror because the mirror and the light are moving in the same direction at the same speed. So which means that if you were to look into the mirror, there's not going to be anything there. You won't be able to see your face. If the light doesn't reach it, obviously it's probably going to be dark, or it's going to have an image of something which is from the past, if there's an image at all. All right, so that's one idea that you can entertain. The second idea is you can place the mirror on a wall inside a reference frame, which is moving at the light speed. All right, so here's your reference frame, which is traveling at the light speed. So this is no for tempo. This thing is moving at the light speed. And then within it, you have light traveling at the light speed. Of course, Einstein is within this medium, so he's also traveling at the light speed. All right, so what would we measure for the light speed, for the light from Einstein's face? Well, if we are using the commonsensical Galilean transformation, we will have to take this speed of light relative to Einstein and add the speed of the reference frame that Einstein is in. And then this is going to give us the speed of light that Einstein, it's going to give us the speed of light that we will see for this particular light traveling from Einstein's face to the mirror. Man, that took forever to explain. All right, so which means that we would experience light in Einstein's reference frame moving towards the mirror, while Einstein is moving at the light speed relative to us. If this light is still moving at the light speed relative to Einstein, this light should be moving at double the light speed relative to us. Except the problem is, according to the second assumption that Einstein came up with, this is postulate number 2. Light should be moving at the light speed relative to you, regardless of your motion. All right, so what this means is this light moving at the light speed relative to Einstein, while he's moving at the light speed relative to us, should still move at the light speed relative to us. At that point, the common sense breaks down. I mean, the common sense, I've been bitching about it forever. Ever since the first day on. I kept saying your common sense is no substitute for education. But that was like the simple stuff. All right. I mean, why do you need a chromosome? Well, it increases the impact, reduces the acceleration. Eventually, you go, okay, so things start to make sense. All right. The stuff that you weren't able to see, eventually you go, okay, yeah, I see it. All right. Eventually, you kind of go along with it, and then it starts to make sense. But this stuff is just a violent violation. It's not even the common sense. It's like the logic completely fails. It's the whole entire math, the structure of math fails. It's bizarre. I mean, how could it be that the light traveling at the light speed relative to Einstein while it's traveling at the light speed relative to us, is still moving at the light speed relative to us. I mean, you can't, your mind just does not grasp, comprehend it. This is so bizarre. All right, and so Einstein also knows that this is bizarre. And that's the reason why he says it's a postulate, guys. It's an assumption. As weird, as bizarre as this assumption is, let's pretend that this is the way the world is. This is the way the universe works. All right, so Einstein is saying, don't question it at this point. I know it's nonsense, but let's play along. Let's play along. Let's pretend this light moving at the light speed relative to Einstein, while he's moving at the light speed relative to us, somehow magically still moves at the light speed relative to you. Well, you're stationary. Then what gives? What happens? All right, so those are the entire relativity based on these two postulates. Got it? All right, so let me just make sure that you understand it, guys. Postulate is an assumption. When somebody says, oh, this is what Einstein said, this is the reason why it's got to be true. Nope. Just because somebody assumes something to be correct does not mean that it is correct. All right. What Einstein says is no significance. It's just like what you say has no significance in sciences. All right. The only thing that we evaluate is the theory when the theory makes predictions. This is a game that we play. All right. Your belief system has nothing to do with it. Einstein comes up with this bizarre idea, completely off the wall. Completely off the wall, as if this guy forgot to take his medication. All right. And then he says, okay, I know this is weird. What I'm going to do is I'm going to take this, make some assumptions, and make a prediction based upon it. And then we'll evaluate the predictions. This is how science is done. So his assumption is, guess what? Regardless of your motion, light travels at the light speed, relative to speed. What that means is if you're traveling at the light speed, with that mirror in your hand, would you be able to see your reflection? Absolutely, yes. You will be able to see your reflection. What if I'm driving my suit.4 Tempo at the light speed? If I were to turn on the headlights, would I be able to see what's in front of my vehicle? Absolutely, yes. Why? Because light always travels at light speed relative to you. Assumption, assumption, assumption. Scientific fact? Not yet, just an assumption. And then he says, what gives? What gives? Seriously, what gives?
In order to simplify the problem he sees with light, Einstein uses a series of thought experiments that take place only in his imagination, like a journey on a train.
From James Clerk Maxwell's equations, we know that the light reflected from my face traveling toward this mirror must move at 186,000 miles per second. Okay, Einstein said, but what if the train were moving at the speed of light?
One possibility is the train catches up to the light waves, so they never reach the mirror. But Einstein is convinced this can't happen. Light can't stand still.
And what does it mean if I do see my reflection in the mirror? Well, from my point of view, everything is just fine. But for the person standing outside of the train, there's a problem. That person sees a train moving by at 186,000 miles per second, and therefore the light reflected from my face traveling toward the mirror must be traveling at twice that rate, or 372,000 miles per second.
372,000 miles per second is the speed of light added to the speed of the train carrying the light. Physicists have added speeds this way since the days of Galileo. But Einstein concludes this simple adding of velocities is wrong, because the speed of light never changes. It's always 186,000 miles per second, even if its source is in motion. Whether on or off the train, you have to get the same measurement for the speed of light. The stunning consequence of this is that someone off the train measures rulers on the train as short and clocks on the train as running slow.
In a flash of brilliance, Einstein proposes that distance and time are not absolute, that a foot and a second measured on the train are not the same as a foot and a second measured off. Distance and time are relative.
So the question becomes, what gives? All right, so what would happen if you're traveling near the light speed? All right, so you got the speed. Speed is the measured distance over measured time. When your speed starts to reach the speed of light, what happens to the distance? It contracts in the direction of motion. It contracts in the direction of motion. If you are traveling to New York City from here at the light speed, how much of the space do you think you're going to be able to see? None, zero. It's going to take a fraction of a second to get there. How much information registers in your brain within that time period? Nothing. You're not going to be able to perceive anything. It's a magic trick. You're looking at the skyline in Chicago, all of a sudden, boom, it's New York City. Things happen that fast. So space is going to contract. Space is going to contract outside of your reference frame in the direction of motion. So space X is going to start to go to zero. It's going to tend towards zero. That's the way we say it. Well, this divided by that should still give you the speed of light, which means that the time, something's going to happen to time. The time is going to slow down. Space is going to contract. Your time is going to slow down. The first one is known as the contraction of space. Remember, the space is only going to contract outside of your reference frame. On the inside, everything is fine. On the outside, boom, everything is going to contract. if you're going across the universe at the light speed, you will not perceive this universe. In fact, the light going across this universe, it's almost like a Beatles song. You won't perceive this universe at all. So in the direction of motion, our universe is not going to exist. So everything is going to contract. This gamma that you're looking at is known as a time dilation factor, relativistic factor that you're looking at. All right, so space, the original space XL that you're looking at is going to get contracted by the relativistic factor that you're looking at. The relativistic factor depends on your speed, which is located here, expressed in terms of the speed of light. So x sub 0 is going to be your proper length. X is going to be your relativistic length, in essence. All right, so the proper length is when you're traveling at the light speed, the proper length is the proper length between here and New York City will be the proper length, and the relativistic length is the length that you will measure for that proper length is you're traveling near the light speed. And then the time is going to slow down. Slowing of time is known as the dilation of time. Dilation means that the time is going to become expanded, which means that the 1 second is going to take longer and longer to occur. So which means that the time is going to slow down. All right, so the time is going to slow down in the reference frame of that particular observer traveling near the light speed, but that person won't be able to notice it. So if you're traveling at the light speed, near the light speed, your time is going to slow down relative to us. Your time is still going to be 1 second long relative to you, and your 1 second time interval may be a minute long, hour long, a year long, 100 years long. All right, so this original time that you're experiencing is going to become elongated. It's going to become expanded. It's going to become dilated, which means that your time is going to slow down, right? The relativistic factor. All right, so TL is known as the proper time. T is known as the relativistic time. All right, so there will be two separate times related to that. All right, so summing up to this point, so the light is always going to travel at the light speed, regardless of your motion. Light always travels at the light speed relative to you, regardless of your motion. Time is going to slow down when you're moving at relativistic speeds. All right, relative to an Earth reference frame, I'm going to say, relative to space is going to contract outside of your reference frame, only in the direction of motion. All right, so these are the
that space flight may one day unlock the secret of time itself.
I believe in 50 to 100 years, we will in fact have rockets that will take us near the speed of light, ion engines, photon engines. They'll take us to the speed of light where time itself begins to slow down. One of the most preposterous predictions of Einstein's theory is that the faster a rocket moves, the slower time beats within that rocket ship. Imagine somebody taking off near the speed of light, and you're sitting on the Earth with a telescope. As you look in your telescope, looking at the rocket ship, you see that everyone inside is frozen in time, because the rate at which time beats has actually slowed down. So we've actually measured this in the laboratory with atomic rockets, with satellites. We can actually measure the fact that time slows down the faster you move.
We've seen this before. Let's watch it again. This is a fun little commercial that I like. Once again, in your own reference frame, everything is going to look normal. But if we were watching you live on TV as you're traveling near the light speed, everything is going to look frozen. The reason is because 1 second may be an hour long in our reference frame, maybe a day long in our reference frame. All right, so in your reference frame, while you're traveling near the light speed, your time is going to still tick 1 second at a time. And if you cannot see the outside, you're not going to experience the contraction of space. And within your own reference frame, everything is going to look the same. All right, so the time is going to tick 1 second at a time, and everything is going to look normal in your own reference frame. If you were to look outside while you're traveling near the light speed, you would notice that you're moving near the light speed because the space outside is going to contract. And if you're watching events transpire live on TV as you're moving near the light speed, all of a sudden you're going to realize that the events are going to start to unfold faster and faster and faster rate. All right, but if you don't have the luxury of being able to see outside or watch TV, then you would never know that you're moving near the light speed. All right, so relative to a stationary observer, a moving clock is going to look slower. So the best answer is the best answer. All right, so now let's talk about the experimental verification. A couple of the experimental verifications of this theory of special relativity. First published in 1905, obviously, and every single aspect of this theory has been tested and tested and tested, proven to be accurate. It's a theory by name only, and theory itself today is considered scientific fact. All right, so one of the experimental verifications of this was 1971 cesium beam atomic clocks experiment.
In 1975, Professor Carol Alley of the University of Maryland,
which got repeated in 1975,
set out to test Einstein's theory with 2 synchronized atomic clocks. One was flown on board a military plane, while the other stayed behind on the ground. After the flight, the clocks were found to be ever so slightly different in the time they told. Time dilation is even more pronounced for the crews on long missions aboard the space station Mir. But what might have remained an obscure footnote in quantum physics could become the most fantastic element of our future in space.
Okay, so while you're traveling near the light speed, if you were to measure your pulse rate, what would you measure? All right, relative to you, the time does not change. Your 1 second is going to be still 1 second long. Your pulse rate is going to be the same. All right, so B is the best answer. So you're in a spaceship. It's got no windows. You got no radios, obviously no TVs. All right, so there's no other means for you to observe or measure what's on the outside, right? And now you're trying to figure out whether or not the ship is stopped or moving at a constant velocity. How can you figure out? What should you do? I got news for you guys. It's called an inertial reference frame. If you got no communication with the outside, if you cannot see the outside, there's no way to tell whether you're moving or you're stationary. Absolutely no way. Because this thing is it's moving in a straight line at a constant speed. So under the circumstance, you can't tell whether you're stationary or moving in a straight line at a constant speed. You just have to give up. All right, so B is the best answer for them.
Even when the theory is as beautiful as Einstein's, it needs testing. And there is a test of relativity in a phenomenon called the decay of cosmic ray mu mesons. A quarter of a century ago, Dr. David Frisch of MIT and Dr. James Smith of the University of Illinois filmed a classic experiment proving the reality of the relativistic time dilation. They did it by measuring the flux through the atmosphere of a radioactive subatomic particle called the mu meson. Created at the top of the Earth's atmosphere by cosmic rays from outer space, mu mesons zoom straight downward at nearly the speed of light. But laboratory experiments, such as the one done here by Smith, show that mu mesons disintegrate naturally after an average life of only 2 millionths of a second. That means that even going at near the speed of light, they shouldn't make it very far through the atmosphere before decaying. Or to put it differently, when Frisch and Smith observed 568 mu mesons in their detector at the top of Mount Washington, they calculate that only 27 per hour ought to make it to the base of the mountain. But when they cart their equipment down to sea level, they find almost as many mu mesons as they had at the top, 412 per hour. Of course, Frisch and Smith really aren't a bit surprised. The reason for the discrepancy is spelled out by the theory of relativity. Traveling at nearly the speed of light, the mu meson's internal clock runs slow so that, as viewed from Earth, they take much longer on the average than 2 millionths of a second to disintegrate. Or, to put it differently, as viewed from the frame of reference of the mu meson, the Earth's atmosphere, rushing upward at nearly the speed of light, is Lorentz contracted to such a degree that the particle can easily make it all the way to the ground in only 2 millionths of a second.
All right, so mu meson, we call it muon in particle physics. Okay, so they have lifetimes. They live 2.2 microseconds before they dissolve into energy. That's what it means. All right, these particles exist only 2.2 microseconds. Microsecond is a millionth of a second. All right, so they come into existence and just as fast, they just vanish. They live 2.2 microseconds. All right, so they are created in the upper atmosphere and created by the energetic particles just colliding with the air molecule. So they come into existence briefly for 2.2 microseconds, and then they just vanish. All right, so they are created. So the muons are going to be created in the upper atmosphere, and they would be traveling about 99.8% of the speed of light at the time of their creation. So they come into existence for 2.2 microseconds while traveling at 99.8% of the light speed. All right, so the distance is going to be 600 meters from the point of their creation all the way to the ground level that you're looking at. So this is the distance that they would be traveling. Let's check to see. This is a book problem. All right. All right, so there are a couple of things that we will have to do. So find on the average how long the muon lives according to an observer on the Earth reference frame, and how far the muon travels before disintegrating. All right, so from our perspective, okay, this is the measurement that they were making. In reality, these things come into existence 4,800 above the ground. That's about 2 miles. 2 miles. And then relative to our reference frame, instead of existing 2.2 microseconds, they actually live 16 microseconds. Okay, so relative to us, it looks like they actually exist for 16 microseconds. So the question is why? All right, so that's what we're going to be looking at. All right, so this is problem number 3 from the handout. It says the lifetime of a muon. So the average lifetime of a muon at rest. So relative to them, they exist 10 to minus 6 seconds. All right, millionth of a second, 2.2 millionth of a second. They are created in the upper atmosphere, and they, while traveling towards the Earth at 99.8% of the light speed. So on average, this 2.2 microseconds from our reference frame. What happens to that? Okay, guys, because they are moving 99.8% of the light speed relative to us. All right, so what's going to happen is their times will slow down. All right, so we will measure that 2.2 microseconds to be much larger than what it is in reality. And then the next question is, how far will the muon travel before disintegrating relative to us? So that's what we're going to be looking at. All right, so let's list everything. So within the reference frame of a muon, all right, so it exists only 2.2 microseconds, 10 to minus 6 seconds. And relative to us, they're moving at 99.8% of the light speed. All right, so what is the time that we measure for their existence? Right, so what's going to happen is the time within their own reference frame is going to become elongated relative to us. It's going to become expanded, which means that their time is going to slow down. All right, so here's the relativistic factor that we're looking at. So relativistic factor is going to be expressed in terms of what you see in the denominator. V represents the speed of a muon, expressed in terms of the light speed. Plug the numbers in, and then this is what we end up getting. All right, so it's going to be 30. It's going to be 3.5 times 10 to the minus 5 seconds. All right, so which means that it's no longer 10 to the minus 6, it's 10 to the minus 5. So which means that the time became elongated, which means that the time slowed down with respect to our reference frame. All right, so without the time dilation effect, okay, if they were to travel for 2.2 microseconds, they would be traveling about 660 meters. It's almost 4/10 of a mile relative to our reference frame. But in reality, because of the fact that their time slows down quite a bit relative to our reference frame, instead of traveling this distance, they travel about 6 miles. So which means that they are able to get to the ground. So that's the reason why the number of muons that they discovered in the upper atmosphere match the number of muons that they detect in the detectors on the ground level. I'm not going to do the derivation. You guys are taking college physics. All right, so now let's go back to the summary one more time. Okay, so what we know. Number one, light is always going to travel at the light speed relative to you, regardless of your motion. So that still stands. Time is going to dilate, which means that it's going to slow down only in the reference frame of a moving object relative to the Earth reference frame. And then the space is going to contract in the direction of motion outside of the Earth. All right, so if you're looking outside, the space is only going to contract in the direction of motion of your reference frame. All right, so let's focus on problem number 4. All right, so we got an astronaut. He's got a meter stick, which means that the meter stick is going to be 1 meter long. And it's going to be 1 meter long relative to a cylindrical spacecraft. Okay, so as it so happens, the length of the spacecraft is going to be 82 meters. And the diameter is going to be 21 meters. Right, so that's what we got. So this spacecraft is moving, and it's moving at constant speed at 95% of the speed of light relative to Earth. All right, so the question becomes, what are the dimensions of the spacecraft as measured by an observer here on Earth? All right, so the original dimensions using a meter stick, obviously it's measured to be, length is 82 meters, diameter is going to be 21 meters. All right, so this thing is moving at 95% of the speed of light relative to Earth. So what would be the measured dimensions by an Earth-bound observer? Okay, guys, I got news for you. The length is going to, in the direction of motion, the length is going to contract. So it's not going to be 82 meters. It's going to be much smaller. All right, the contraction is going to take place only in the direction of motion. So the contraction is going to take place in the direction of motion. So the length is not going to be 82 meters. It's going to be smaller than 82 meters. And the area, all right, it's not in the direction of motion. So you're looking at a cylinder. It's got capped by two areas. Those areas are not in the direction of motion. So which means that the diameter is going to remain the same. So in the direction of motion, this thing is going to look contracted, but its diameter is going to remain the same. So that's what we should come up with if it's done correctly. So contraction of a meter stick is what we're looking at. So the length is going to be 82 meters. The diameter is going to be 21 meters. This thing is moving at 95% of the light speed. So what are the dimensions that we measure for this spacecraft from an Earth reference frame? So let's list everything. Diameter, DO, is going to be the original diameter. It's going to be 21 meters. LO is the original length. That it's 82 meters for this spacecraft. It's moving at 95% of the light speed relative to us. So what is the length that we measure for it relative to us? And what is the diameter that we measure for it relative to us? So like I said, the contraction is only going to happen in the direction of motion. So the length is going to contract. The diameter is not going to change. It's going to be 21 meters. The length is going to get contracted. Obviously, you can figure that out. We know the original length divided by the relativistic factor. There's your relativistic factor. And so it's going to be about 26 meters. So what is the original 82 meters? It's going to, from our perspective, it's going to look like it's 26 meters. That's what I think.
As the light leaves the star and the star wobbles, the spectrum of light from blue through red shifts back and forth in space, and that Doppler shift of the light back and forth tells us that, in fact, there's a planet yanking on the star.
As the star wobbles towards the telescope, its light goes blue. As it wobbles away, red.
And that amount of Doppler shift allows us to determine the mass of the planet and the orbit of the planet. As the
All right, so here's the relativistic Doppler shift. When the planet is moving away from us, it's going to look reddish. Moving towards us, it's going to look bluish. All right, so
if a galaxy is moving away, its light is stretched.
This happens because of the fact that the light moves at the light speed relative to
the interval between wave crests gets longer.
So if it's moving away from us, the wave is going to become longer. The wavelength is going to get larger. If the wavelength gets larger, the frequency is going to go down. All right, so it's going to look reddish. If it's moving towards us, the wavelength is going to get shorter, and the frequency is going to get larger. So it's going to look bluish as a result.
The light appears redder. The faster it's moving, the redder the light. If a galaxy is moving closer, the light is compressed and appears bluer.
All right, so relativistic Doppler shift is the way we know that there's contraction of space.
In addition to revealing a star's composition and temperature, stellar spectra offer clues about the motion of stars.
In the last century, it was discovered that the wavelength of light could be changed, or would be changed, if the object emitting the light was moving toward the observer or away from the observer. And this has become known as the Doppler effect for one of the earlier studiers of this effect. We can also hear it in sound. The pitch of sound depends on whether something is approaching us or receding from us.
The Doppler effect also applies to stars and starlight. If a star is approaching us, then the light coming from that star will be slightly shifted towards the blue end of the visible spectrum. And so we can compare a laboratory spectrum with the stellar spectrum, we would discover the line slightly shifted. The amount of shift is directly related to the speed at which the star is approaching us. On the other hand, if the star is receding away from us, then the shift of those spectral lines will be slightly towards the red end of the spectrum. We would say it's a red shift.
It's pretty incredible. 100 light years away, there's a star. You can barely see it. It's dim. But you can measure by looking at the shift of these lines exactly how fast it's moving.
We can also determine how fast the star is rotating. Imagine a star that is spinning around its axis this way. As this side rotates towards you, those lines will be, on that side of the star will be Doppler shifted to the blue. On this side, which is moving away from you, those lines will be Doppler shifted to the red. That makes the whole absorption line much broader than it otherwise would be. And so from the width of the line, we can tell how fast the star is rotating.
So the Doppler shift is used throughout astronomy, even to measure the speeds of galaxies halfway across the universe, which move at substantial fractions of the speed of light.
All right, so relative to a stationary observer, a moving object is going to appear shorter than normal. So C is the best answer for that one. So we have a moving object, and it's moving parallel to its length. And then it's approaching the light speed. So the length of this object is measured by a stationary observer. It's going to tend towards 0 in essence. So it's going to look like it's approaching 0. A is the best answer for that one. So it's going to look contracted. The width of the subject is not going to change. The contraction only takes place on the direction of motion. So the width is not going to change. So the best answer is B. All right, so traveling at the light speed. So what's going to happen to space? Space is going to contract. All right, so if you reach the light speed, what happens to space? So the V is going to be the same as the light speed. So here's the contraction of space. All right, so V turns into C. C divided by C is going to be 1. 1 minus 1 is going to be 0. So what that means is the space is going to contract to a point at the light speed. So the space contracts to a point at the light speed. If you're traveling at the light speed across the universe, you will not perceive this universe. You would go right across the universe without noticing that there's a universe that you're going through. So the light traveling at the light speed across this universe does not perceive our universe. As far as light is concerned, we do not exist. All right, so that's one conclusion. The second one is also really bizarre. So what happens to time if you're traveling at the light speed? So V is going to become C at the light speed. All right, so 1 minus 1 is going to be 0. Anything divided by 0 is going to be infinitely long. So 1 second in your reference frame is going to be infinitely long in our reference frame. Okay, so which means that time is going to stop at that point. All right, so the relativistic time that we measure for your 1 second is going to be infinitely long from our reference frame. So oddly enough, what that means is the light, while it's traveling across the universe, it's not going to perceive our universe. And the light itself, it's just a particle, guys. When we get to particle physics, you will notice it. And most of these particles, like muon exists within 2.2 microseconds before it disintegrates. It's its own reference frame. It's just a flash. It comes into existence and just as fast it's gone. Because it's moving near the light speed, now that 2.2, microsecond, we experience it as 16 microseconds or something. All right, so, but imagine that the light is probably just like muon. It probably barely exists within its own reference frame. Maybe it exists within a trillionth of a second. Maybe it exists within a quadrillionth of a second. But because it's moving at the light speed relative to us, that thing that barely exists in the universe looks like it's got a permanent existence relative to us. And why is this significant? Guys, the reason why this is significant is the universe is created out of energy. Light is energy. It may not even exist within its own reference frame. And while it's traveling across this universe, we don't exist according to light. And within our reference frame, what looks like something eternal may not even exist its own reference frame. Okay, so welcome to reality. Given the fact that everything is created out of energy, everything is created out of light. Right? I was saying, oh, this is so weird. It is really weird. Light travels at the light speed relative to us, so it's got a permanent existence, despite the fact that within its own reference frame, this thing probably does not even exist or barely exist. If it does exist, it probably exists like 10 to the minus million seconds, if not less than that. It's weird that
what Einstein did was completely turn the problem on its head. Other scientists had found it impossible to accept Maxwell's idea that light would always move away from you at 670 million miles an hour, even if you too were traveling really fast. But Einstein just accepted that as a fact. Light's speed never, ever changes. Then, what he did was bend everything we know about the universe to fit light's fixed speed. What he discovered was that to do that, you have to slow down time.
His extraordinary insight is that time, as you approach the speed of light, time itself will slow down. It's a monumental shift in how we see the world.
The very instant when Einstein had this brilliant insight that time could slow down, well, the floodgates began to open. You see, before then, people had assumed that time was like a wristwatch on God's hand, that it beat at a steady rate throughout the universe, no matter where you were. Einstein said no, that the tick, tick, tick of this wristwatch was actually the click, click, click of electricity, turning into magnetism, turning into electricity. In other words, the steady pace of light itself.
90 1905 was a miraculous year for Einstein and for physics. He had an unbelievable outpouring of creativity. It starts with his publication of a paper on how to work out the true size of atoms. 2 months later is the publication of his paper on the nature of light. That's what we'll learn of the Nobel Prize. But the third paper, only a month later, is on how molecules move when heated, and that finally ends the debate on whether atoms really exist. The fourth paper is published at the end of this half-year period. In it, Einstein sets out his theory of light, time, and space. It was the theory of special relativity. That changed the way we see the world.
In Einstein's new world, the one true constant was not time or even space, but light. But Einstein's miracle year was not over. In one last great 1905 paper, he would propose an even deeper unity. As he computed all the implications of his new theory, he noticed another strange connection, this one between energy, mass, and light.
Einstein realizes that the speed of light is kind of like a cosmic speed limit. Nothing can go faster. So imagine we have a train charging along, and let's say it's getting up at the speed of light, and we're stuffing more and more energy in, trying to get it to go faster and faster. But it's still bumping up against the speed of light. So all this energy, where does it go? It has to go somewhere. Amazingly, it goes into the object's mass. From our point of view, the train actually gets heavier. The energy becomes mass. It's an incredible idea. Even Einstein is amazed by it.
I think I have found a connection between energy and mass, if I am right. And energy and mass are not absolute. They are not distinct. They can be converted into one another. Energy can become mass, and mass can become energy. And not just energy equally mass. Energy equals mass times the square of the speed of light.
Would you like me to check your mathematics?
Einstein sent his fifth great 1905 paper for publication. In 3 pages, he simply stated that energy and mass were connected by the square of the speed of light. E equals mc squared. With 4 familiar notes in the scale of nature, this patent officer had composed a totally fresh melody, the culmination of his 10-year journey into light.
Here we are for thousands of years thinking that over here is a world of objects, of matter, and over there is an entirely separate world of movement, of forces, of energy. And Einstein says, no, they're not separate. Energy can become mass, and crucially, mass can also become energy. There's a deep unity between energy, matter, and light.
E equals mc squared. That equation shows that every piece of matter in our universe has stored within it a fantastic amount of energy. The speed of light, for example, is about 300 million meters per second. You multiply that by itself, and you get 90 quadrillion. So in other words, what is matter? In some sense, matter is nothing but the condensation of vast amounts of energy. So in other words, if you could somehow unlock all the energy stored within my pen, that would erupt with a force comparable to an atomic bomb.
After Einstein's fifth great 1905 paper, physicists no longer spoke of mass or energy. They're now the same thing to us.
Probably the most miraculous year in science ends in silence. The articles are published to resounding.
So when you start to approach the light speed, time slows down. Space is going to contract in the direction of motion. And all of a sudden the question becomes, wait a minute. So the time slows down near the light speed, and the space is going to contract along the direction of motion. But what prevents us from going at the light speed? All right, so what's the significance of light speed? Why is it possible to travel at the light speed? Becomes a question for Einstein, and he starts to ponder about it, only to realize that when you're stuck putting energy into something and trying to get it to move at the light speed, closer you get to the light speed, the more massive you will become. Which means that the energy that you put in to the mass in order to get it up to the light speed is going to start to go into its mass rather than its speed, in essence. And all of a sudden, he's thinking, wait a minute, is it possible that the mass is a form of energy? All right, so that's how the equation E equals mc squared comes about. So you got your mass, so which means that when you start to approach the light speed, you will become more and more massive. So that the energy that you put in order to accelerate something is going to start to go into its mass. So what would happen if this mass is moving at the light speed? If it's moving at the light speed, it's going to become infinitely large. So, or it will become infinitely massive. So which means that the energy required for it to move at the light speed would be infinitely large. Okay, I think that's the next discussion. Let's move on to the next discussion. So E equals mc squared means when you take a mass. All right, so this is your rest mass. M is the original mass. This is known as the relativistic mass. All right, so your relativistic mass is going to depend on your speed. As you start to approach the light speed, obviously you're going to become more and more massive. So at the light speed, the amount of energy required for you to travel at the light speed is going to be infinitely large. That's what it means. Now, the amount of energy available in the universe is finite in size, as far as we know, because the universe started out with a Big Bang. So the amount of energy required for you for any mass to travel at the light speed is going to be infinitely large. So what that means is that there would not be enough energy in the entirety of the universe for any mass to travel at the light speed.
And your mic is distorted.
Is it better?
Yes, yes.
Awesome. Give yourself 5 points for that one. Let's hide this away.
Nothing can travel faster than light.
Why, you may ask? The special theory of relativity says that as you approach the speed of light, your width flattens to become infinitesimal. If you broke the speed limit, your mass would be infinite, and that's impossible. And you would need infinite energy. And in the whole universe, there's not infinite energy.
Okay, I'm just trying to decide whether or not I want to do this. Okay, let's do it anyway. All right, so what do we have? We got a Gauss ball. All right, so the mass of the Gauss ball is given. So find the rest energy of the Gauss ball. And then if we were to turn this rest energy to operate a 75-watt light bulb, how many years this light will be operational? So that's what we're going to be looking at. All right, so here's the rest mass of the light bulb. All right, so what's the energy of it? So the energy of it is going to be E equals mc squared, obviously. Plug your numbers in, so and then you're going to get an answer in terms of joules. And so the power of the light bulb is given. What's the power? The power is going to be 75 watts. Power is how fast energy converted, how fast energy is transferred. So it's going to be E divided by T, amount of energy per time, solve for time. So it's going to give us the time in terms of seconds. And then convert it to years, I think. That's going to be 1.8 million years. So if you can convert the mass of a Gauss bulb into electricity, this light bulb will be functioning for that many years.
Every gram of matter contains a tremendous amount of energy. But if none of that energy escapes, none of that energy can be observed. It's like a fabulously rich man who never spends anything. No one can tell how rich he is.
And if mass contains energy, then energy has mass. Every second, the Earth is struck by 4½ pounds of sunlight.
All right, that's interesting. 4½ pounds of sunlight. All right, so this is the amount of energy being radiated by the sun per second, in essence. All right, so this is per second, so that's the power being radiated, amount of energy radiated per second. So this is expressed in terms of watts, so that's 10 to the 26 watts. 4 times 10 to the 26 watts. So the question is, obviously, this is the amount of energy being radiated, which means that the sun is losing mass because of by the amount of energy that it radiates. So what is the change in sun's mass per second? Well, it's radiating this much. This is the amount of energy which is being radiated by the sun per second. All right, so this is the mass of the sun. It's going to be 2 times 10 to the 30 kilograms. So what fraction of the sun's mass is lost within a human lifespan, which is about 75 years? So that's an interesting question. So the power of the sun, this is the amount of energy being emitted by the sun per second, expressed in terms of watts. So which means that the energy being emitted is going to be coming out of the mass of the sun. So what is the amount of change in mass of the sun within a human lifespan, which is about 75 years? All right, so we're looking at the change of the sun's mass relative to its original mass within 75 years. So 75 years expressed in terms of seconds, so that's a big number. All right, so this is the amount of energy being emitted in terms of the amount of mass being emitted by the sun. This is the change in mass that we're looking at. All right, so the power is given, so for the change in energy. And change in energy is going to be expressed in terms of the change in mass. All right, so let's just do a back substitution here. All right, so delta E is the same as PT, and which is the same, and then there's change in mass, C squared. So isolate the change in mass. That becomes the final equation as it so happens. All right, so we know the power being emitted by the sun. T is the human lifespan, roughly about 75 years. C is the speed of light, plug the numbers in. All right, this would be the amount of mass that the sun would be losing within 75 years. So we'll express it in terms of the total change in mass. That's almost, yeah, this is 968 million pounds of mass being lost by the sun per year. All right, so fraction of the sun's mass would be lost within a human lifespan. So that would be a very tiny fraction of the sun's mass would be lost within a human lifespan. So that's what it means. So the sun is going to be around for. All right, so as the velocity of your spaceship increases, you would observe nothing. Everything is going to look the same from inside. Your clock is going to run its own regular rhythm, 1 second at a time. Your mass is going to feel the same. All right, so none of the given answers are correct.
As a teenager, our next person of the century was puzzled by the nature of light and set out to fathom its mysteries. Albert Einstein's discoveries about light, matter, and energy would revolutionize science. The speed of light, he proved, is absolute, but time and space are not. We live in a strange universe in which things change size and weight depending on their speed, in which time itself is relative. By the 1920s, he was the most famous scientist in the world, once asking, why is it nobody understands me and everybody likes me? He loved music, Bach and Mozart. He figured out the mysteries of the universe, but couldn't make a can opener work. His hairstyle, he said, he got through negligence, and once wrote, if I were to start taking care of my grooming, I would no longer be my own self. So the hell with it. Einstein's most famous equation expresses the relationship between matter and energy.
All right, so the conclusion is nothing with mass, nothing travels at or faster than the speed of light. Of course, light travels at the speed of light. Time is going to dilate or slow down for an object moving within the object moving at the light speed. And space is going to contract only outside of your reference frame while you're moving near the light speed. And mass is a form of energy. That's it. Only one that required correction is the first one.